Hello, today we will discuss about laser. So first let me talk about what is laser. In simple way, the abbreviation of laser is light amplification by stimulated emission of radiation. So in this discussion we will talk about what is the meaning of amplification and what is the meaning of stimulated emission and what is the process of radiation. Actually, around 1917, Einstein gives the idea about laser, about the light amplification, or mainly he gives the idea about stimulated emission. But experimentally, the first laser was built around 1916. Now to know about laser, so first you have to know about the process of absorption and emission in case of atomic system. So in atomic system, there will be electron arranged in different energy states. If electron transit from one energy state to another energy state, it need to absorb some energy or it need to release some energy. So our first process is absorption. So in this absorption process, the energy will be supplied. Now look at this picture where we have depicted the absorption process. Now two energy levels are given, electrons are placed here, we are supplying some energy. After absorption, electron moves from ground state to excited state. Now comes the case of spontaneous emission or the cases of emission. After absorption, electron starts moving from ground state to excited states. In this process, it will going to lose the absorbed amount of energy. So, after some time, it must come back to the ground state again. And in this process, what was the absorbed energy? This will be released. And obviously, released energy will be in form of photon. Now, in normal process, there is an emission which is known as spontaneous emission. This is also known as random emission. So one can think about a case when there will be random absorption and there will be random emission. Although the amount of energy will be same in each and every emission, every spontaneous or random emission. But as they are not happening at same time, so their properties, mainly the phase properties of the photon, are not same. The time taken of this process is very less. This is in the order of 10 to the power minus 8 seconds in normal cases. Now Einstein thinks about another types of emission which is known as stimulated emission. In case of stimulated emission, the electron will absorb the energy, it will transit from ground state to excited states, and when it is somewhere here in the process of transiting from ground state to excited state, it will absorb some additional energy. Now when time period is over, it will come back to the ground state, and in this process this will going to release two photons. Earlier it was absorbed in the ground state, and another it may be absorbed in anywhere in between the ground state to excited state. So here it will release two photons. Two Hν will come out from this. Now comes the most important part, which is known as the Einstein's AB coefficient. Now to know about Einstein coefficient, Einstein was trying to explain that total rate of absorption is equal to total rate of emission. This is the obvious process. How much energy will be absorbed, this much energy will be released. Now there will be absorption part and there will be spontaneous emission and stimulated emission. Now we should know what are the dependent parameters for the absorption and the emission process. So absorption is a process. It obviously depends on two important things. One is how many number of particles are there in the ground state, say this is N1, and how much energy you are supplying to the system. Instead of considering the energy, rather we'll consider the energy density. So let me just represent it by E nu. So here energy is in form of photons. So it's a function of frequency. That is the cases of absorption. So the rate of absorption depends on these two parameters. Now the emission, spontaneous emission, it's a random process. But the case is the emission process is purely depends on how many number of particles are there in the excited state. If more number of particles are there, the process of spontaneous emission will be more, and if this is less, obviously the spontaneous emission process will be lesser. So the spontaneous emission or rate of spontaneous emission, it depends on how many number of particles are there in the excited state. Say this is N2. So in the spontaneous emission case, there is no chances of energy absorption. So it's not depending on the energy. Now comes the next part. Is the stimulated emission. Now stimulated emission, it depends on how many number of particles are there in the excited state. Obviously, if there are more particles, you have a chances of coming back from excited to ground state. And obviously, it is absorbing some amount of energy in between the path. So, it also depends on energy density. So, the stimulated emission, it depends on N2, number of particles in the ground excited state, and energy density. So, one can write the equation for absorption is equal to emission, spontaneous emission plus stimulated emission. So in this process, just look at this, the spontaneous emission, actually first is absorption. So absorption depends on number of particles and energy density. Then comes the next case of spontaneous emission. Spontaneous emission is only depends on number of particles in the excited state. And stimulated emission, it depends on number of particles in the excited state and energy density. As the rate, they are proportional to these factors, so the proportionality constant was considered over there. So absorption proportionality considered as B12. Why this is 1, 2? One can just refer this picture. So here we have considered this is state 1 and this is 2. So your transition in case of absorption, let me just consider this thing. This is 1 and 2. So your transition process is from 1 to 2. So the absorption is proportional to N1 and energy density. One can write H also, as H is constant, so every time I am not considering this thing. And the proportionality constant is considered as B12. So the next step one can write this is as, so this is equal to B12. So B is a constant, depends on the system, and the direction of the transition is 1 to 2. Same way, the spontaneous emission. The spontaneous emission depends on number of particles in the excited state, which is N2. This is proportional to this. And the proportionality constant is given as A21. Why this is 2-1? Now transition happens from 2 to 1. Next is the stimulated emission. Now stimulated emission, it depends on number of particles and also energy density. And the proportionality constant is given as B21, again from 2 to 1 transition. Now you have the equation for absorption. The rate of absorption is there. This is equal to rate of emission. So this is spontaneous emission and this is stimulated emission. Now you can see number of parameters are equal in left side and right side. So let me just arrange all of them. So after arranging all of them, one can get the energy density relation. So energy density now can be expressed in this form: A by B divided by N2 by N1, 1 divided by 1 minus B21 B12 N2 and N1. Now this is the energy required or energy density for the process of electron transition from state to another state. Now when this equation was arrived in this form, Einstein started comparing this equation with the famous Planck's equation. Now you can just take two of this thing. This is Einstein's equation and this is Planck's equation. So in this expression, so number of particles n2 by n1, it is having a relation. This was given by Boltzmann equation, where n2 is equal to n1 exponential energy difference h nu, in this case energy is h nu divided by L1 minus. So if you rearrange the thing, one can get an expression something like this from the Einstein's calculation. And this was the famous Planck's blackbody radiation expression for radiation. Now when they are comparing, when this equation 1 and 2 was compared, it is showing that they are of same form. So one can take the comparison and find the coefficient values from this. Obviously when you are comparing these two, A by B becomes 8 pi h d cube divided by c cube. And obviously this factor becomes 1. So this was the importance of Einstein's equation. It really explains the process where you have stimulated emission and the next case of the radiation process. So what is the importance of stimulated emission? The importance of stimulated emission is that it is a process where you can increase the number of photons. And obviously in a same transition you are getting two photons, and the two photons are absolutely same properties. Now can you really get this thing? Can you really get a stimulated emission? Now to get this thing, we'll try to calculate the rate, a ratio between spontaneous emission to stimulated emission. Just look at this picture R, the equations I have written. So this is the rate of spontaneous emission and this is the rate of stimulated emission. This is, both the cases are emission, so this will be N2 by N2, so N2s are managed, they are adjusted with this thing. And now we can simplify this one. Just A by B, we know what is A by B. Okay, so A by B factor is this thing. And also when you have energy density, you have the same expression multiplied with 1 by this particular factor. So one can write your R is of in this one. Now if you try to calculate this one, if you try to calculate this thing, one can consider the room temperature. T is around 300 Kelvin, and one can take frequency in the optical range so that we can get the light. If you put this thing, it is observed that the rate, what is the rate? The ratio between spontaneous emission and stimulated emission is very, very high, is in the order of 10 to the power 8 something. So this order is very, very large. So to get one stimulated emission, you need to take a 10 to the power 8 number of spontaneous emission. So obviously for the optical range, you will never get a high level of same property photons. So theoretically the stimulated emission is possible, but naturally you have a restriction for the optical regions. Now how one can achieve a stimulated emission process to get a highly intense light source? So for that case we will follow some of the process. Now to get this thing, one can use the concept of population inversion and metastable state. Normally around room temperature or at thermal equilibrium, the equation, the relations between number of particles in ground state and excited state, actually you can consider the lower and excited level, you have a negative exponential relation. So it really says that in the lower level there will be more number of particles in comparison to higher level states. So naturally you have this restriction. Obviously this was the process what we have proved this thing in case of our calculation. Now if it is possible to get another state, what will be considered as a metastable state, which will be in between the ground state and excited state. Say this is somewhere here. So you need to choose a system where you have a metastable state and particle will transit from ground state to excited state via metastable state. Now let me just understand what is population inversion here. Now normally in thermal equilibrium, the populations are arranged something like this. So obviously in the ground state there will be more number of particles in comparison to excited states. But in case of population inversion, if you can achieve this thing, one can get more number of particles in the excited state. So how to achieve this thing? How to achieve this thing? So if you are able to achieve this one, if you are able to achieve number of particles, more number of particles in the excited state, so obviously the stimulated emission process will increase. And if the stimulated emission process is increased, so one can amplify the light. So how to achieve this population inversion? So to achieve population inversion, one can use the concept of pumping. So what is pumping? So to get pumping, just to think about ground state, excited state, and somewhere here there will be metastable state. So our motto is to get more number of particles in metastable state. But as the spontaneous emission is dominating, particles will move from ground state to excited, and from excited it will directly come to ground state. Now to stop this thing, we'll force them to move from excited state to ground state. So what we'll do, we'll give some energy, so there will be process of absorption. Particle will move from ground state to excited state. When they are here, they are about to come back, we'll stop them to move to ground state. Rather, we'll force them. We'll use the concept of pumping to force them from excited state to metastable state. If you are able to do this thing, then we will be able to achieve what is called population inversion. Now, the metastable states, the choice of metastable states or choice of the medium plays a very, very important role here. So you must have to choose a metastable state whose time period must be greater than the ordinary emission process or ordinary excited process. Just remember, in case of spontaneous emission, we have mentioned the time taken is in the order of 10 to the power very small time. But the metastable state should have a high time. So this is in the order of say 10 to the power minus 5 seconds. So for a gap of 10 to the power 3 seconds, approximately 3 seconds, so there will be gathering of some particles. So for a fraction of time, there will be some number of particles. This may not be very large, but there will be sufficient number of particles is stored over there. When the particles are stored over there, then what happens? Then the process of population inversion is done. So in the population inversion, what happens? This number of here, the number of particle is more. So when time is over, particles will come back continuously. So what happens in pumping? So pumping, you are applying some energy. So this is not pumping, this is a process of absorption. The particle will move from ground state to excited state. Now here you have to use the concept of pumping. Here we need to use the concept of pumping. Pumping helps the particle move from excited to metastable state. Now what happens in this case? there will be no loss of energy. So pumping is a non-radiative process. It just helps to move from excited to metastable state. Now when time is over, the continuously particles are coming from excited state, that's mean in this case the metastable state, to ground state, and continuously the photons are coming out from this. So in this process we are able to increase the process of stimulated emission. So as you have increased the stimulated emission, artificially at least you are able to increase the stimulated emission, so the number of photons will increase, and obviously they look like a single transition. It's a pseudo single transition process. So now how many number of photons are coming? They are of same properties. They are identical property photons are there. So identical properties means their phase values are equal. So to get a laser, you need to achieve population inversion by pumping and metastable state. So these are three important parts for lasers. So as you have a natural restriction for laser, for stimulated emission, so one can get a artificial way to produce stimulated emission by pumping, by population inversion and metastable state. So there are different types of pumpings are available. There may be optical pumping, electrical pumping, then atom-atom collision pumping. Okay, there may be thermal, there may be chemical. So different types of energies can be used to help the particle moves from excited state to the metastable state. Now you need to have a threshold condition. So obviously the threshold condition is about the metastables. It's a metastable state. So threshold condition is the lowest excited level. Okay. So the lowest excited level plays a very, very important role. That means this is the metastable state. Okay. Which gives us the stimulated emission, rather spontaneous emission. So the stimulated emission is dominating here. Now to achieve population inversion, one must use a device which is called optical resonator. So optical resonator is a system where you have an active medium, that's mean the laser cavity, laser medium. So there may be different types of laser. There may be helium neon laser, there may be ruby laser, there may be carbon dioxide laser. So this material will be there inside this tube. And now you need to supply some energy. So when energy was supplied, the photons start producing. So obviously the initial cases, there will be very, very less percentage of stimulated emission. Now the stimulated emission, photons, produce photons, they are moving in all directions. Okay. Now what you will do, you will use two mirrors over there. The photons are coming, they are moving in any of the directions. Now as they are moving in different directions, they will be reflected back by these mirrors. When they are reflected back, so the photon or the combination of photons, the waves, they will interact with each other. Now the adjustment of the mirror, the length of the mirror, the length between the mirror plays a very, very important role. So your adjustment will be something like this, so that you can get a proper lobe over there. So you will get a pattern of, well, let me just take different color. I can take green color here. Okay, you can think about this line. So now when the photons are interacting with each other, they are forming some sort of sinusoidal superposition like this. So every time it may not be sinusoidal, but for simplicity one can think about this. It may vary. Instead of 2 lobes, now you will have 3 lobes, you will have 4 lobes. But what is the advantage of this lobe? So here at that point, the amplitude values are maximum. Here amplitude values are maximum. So light intensity is maximum. It is proportional to A square. Actually this is intensity is maximum when this is A plus A whole square. So this is the additional energy which helps us for pumping the system. This helps, this additional energy, this extra energy helps the particles to move from excited state to metastable state without any loss in the system. Now when they are in the metastable state, time is over, particle will come back to the system. So optical resonator plays a very, very important role to produce lasers. Now lasers are very, very important one. So the shape of the mirrors will be different from different systems. This may be plane mirror, then may be concave mirrors, okay, and there may be combination of plane and concave mirror, and the distance between the mirror, this will also vary to have a better performance of laser. So every time when we have superposition of two photons, two waves, you must have to take care about this thing. The frequency difference, say the frequency difference I am representing as, say, delta nu. It must be equal to velocity. So when you are talking about light, photons, that means C divided by 2 of L. What is L? L is the length of the optical resonator. What is the length of the optical resonator? This can be detailed. They will be in contact with them. So we have this one. So you need to satisfy this relation. This will be equal to certain integral values. Certain integral values, as you have integral lobes. What picture we have considered? We have two lobes over there. Okay, two lobes. Let me just have a better picture. Okay, so this will be equal to twice of phi. Okay, if this is 3, so then it will be 3 times of phi. This may be 4 times of phi. This will be n times of phi, the discrete values it will take. This is basically n into phi. Now there are two types of resonator modes are available. One is longitudinal modes, another is transverse modes. So the frequency values are different in case of longitudinal, and in case of transverse, both frequency and intensity of the light, they will be different. Now optical resonator will produce large number of photons. The photon properties are same, they are coming out, they are interacting. But when they are interacting, obviously in between you will get a laser. Now what you will do, you will get, this is as a 100% reflector, highly reflected in. But here what we will take partially reflected. So through this partially reflected, some of the photons are transmitted through this. This is the output laser. Okay. See here you have 100% reflectivity. That means that all the photons are coming out after reflection, and here maybe 98%. 98% photons are reflected back. Only 2% are coming out from this. So every time this is not 2%. This will vary depending on the laser system. But this 2% will be sufficient. You will have a large number of photons are coming, and the photons are all the photons having same properties, same phase values. So let me just talk about the properties of lasers. So the first and one of the important thing is directionality. So what happens in case of directionality? For ordinary light, light waves moves like this. It forms a cone over there. So then some number of photons are coming. So obviously if the distance from source and screen is L1 and say this is L2. Now L1, if the radius of the screen is R1, it's a circular path. So the area is pi r1 square. And here this is r2. I am considering the second one is, so area is pi r2. So obviously pi r1 is greater. Say this is a2 and this is a1. So obviously a2 is greater than a1. Now here for the ordinary light, the area increases as the distance increases. So the photons are coming out from the ordinary light source. They are divergence in nature. They are moving in a straight line, but they are in a divergence form. They are moving in different directions. It forms a cone. Now here at L1 distance, the number of photons, and L2 distance, number of photon is same. So here number of photon is say n, here also number of photon is same. So what happens about the intensity? So intensity can be calculated as n divided by A. So this is A1. Obviously here intensity is more. Okay, as A is lesser, so intensity value will be more, and here A2 is more, so intensity value will be less. So for ordinary light, as light covering some distance, so intensity decreases. The same thing happens for laser, but in a different way. What happens in case of laser? These beams are absolutely same properties, so the distance between the beam is very, very less. Now the area here and area here is almost same. So the intensity at that point and intensity at that point, they are almost equal. So highly directionality gives a high intensity of the thing. So number of photon increases, and along with this one, this is not divergence in nature. So laser gives the advantage, high intensity and high directionality. Now comes these two cases, monochromaticity and coherency. Obviously we have the artificial stimulated emission. It's act like a single transition. So single transition gives single type of photons and single phase values. In simple words, what happens? A recapitulation. So two energy states, particles are here, there will be absorption, particle moves from ground state to excited state. After absorption, then it comes back and there will be process of emission. Now if some energy is absorbed here also, so there will be two photon release. So this is the case of stimulated emission. So there are two things, absorption and emission, spontaneous emission and stimulated emission. Naturally, stimulated emission is not for ordinary light around room temperature. So we will not get a high intense laser. Although this is good for human beings. But to get laser, what you have to do? We have to get the state of population inversion. How will you get population inversion? You need to take a metastable state. Now you need to apply some energy, particle will be absorbed, this will move from ground state to excited state. Now here you need to force the particle to move from excited state to metastable state. So in this process, this becomes pumping. Now when you have pumping, then you have the states of pumping from excited to metastable state. Now after metastable state, when time period is over, particles will come continuously from metastable state to ground state, and continuously photons will be released. And the photon properties are similar. Their phase values are similar. So we have a high coherency, and also they have high monochromaticity. Single photons were released as you have a single transition in this case. Okay, number of photon increases, so it is high intensity, and high redirectionality, that it is not divergence in nature. Okay, so this is all about